Hello everyone, my name is Ji Kaiyang. Today my presentation is about German signal recognition that we call time frequency analysis and convolutional neural network based Fuze German signal recognition. Next, I will explain the above 5 parties to you. First is the introduction, followed by German signal recognition with CNN. This side generation and offline training, simulation results and analysis, and finally the conclusion. Fields play an important role in electronic warfare nowadays, with the continuous development of jamming means the development of intelligent field anti-jamming is imminent. No, the recognition of field jamming signal is a prerequisite to realize intelligent field anti-jamming. In order to enhance the anti-jamming ability of the fields, first we should accurately recognize the field jamming signal. Traditional field jamming recognition schemes usually accomplish the recognition by manually extracting the signal features in their time or frequency domain. However, the accuracy achieved by traditional recognition methods is limited. Moreover, extracting the features of the field's jamming signals by traditional methods becomes more and more complicated and is hard to be practically implemented. To address the limitations imposed by traditional methods, we propose a field jamming signal detector based on time frequency analysis and a convolutional neural network. We call it TFI-CNN. Next is the system model. From the figure, we can see that the FM radio field jamming signal recognition system includes the target detector, the jamming source, and the jamming signal recognition module. The target detector sends the field signal by FM expressed as this, where U is the transmit signal amplitude, omega 0 is the carrier angle frequency, delta omega is the maximum frequency shift, and omega m is the modulated signal frequency. Then, the transmitted field signal reaches the target. After the target reflection, the field echo signal is formed and expressed as this, where you see is the field echo signal amplitude, tau is the delay time, r is the distance between the field and the target, and c is the speed of light. After being interfered by the jamming sources, the signal obtained at the target detector receiver can be written as this, where GT is the jamming signal and NT is the AWG. From this figure, we can see the process of field jamming signal recognition. The received signal is further mixed with the local oscillator signal that matches the carrier signal and enters the jamming signal recognition module. The jamming signal recognition module consists of two parties, the TFA module and the CNN detector. The TFA module converts jamming signals into time frequency measures. The CNN detector extracts time frequency measures features and recognizes the jamming signals correctly. Next is data preprocessing. In order to extract more features from a one-dimensional time series signal, we adopt the TFA method, where the short-time Fourier transform is designed to acquire the time and frequency domain characteristics of signals simultaneously. The STFT of the discrete signal Xn can be written as this, where Jn is the window function. Since the time frequency measure is obtained by transforming the signal processed by the STFT sliding window function, the time and frequency domain resolutions are not available at the same time. To avoid the serious distortion, we choose hand window and set the length of the window function to be 256. Moreover, we set the OLI part of the window function as half length of the window function. The figure shows the structure of the TFASN detector. The TFASN detector consists of 4 convolutional layers, 2 polling layers, and 2 fully connected layers. The detailed configurations of the convolutional and polling layers are shown in Table 1. To reduce the complexity of the proposed detector, we use 1 multiply 1 convolution between convolution layer 2 and 4, and reduce the number of feature channels to limit the training parameters. The first fully connected layer has 512 neurons, and the second fully connected layer as the output layer has 15 neurons, representing 15 German signals. All the layers use the ReLU activation function, except for the second fully connected layer that takes the softmax activation function. To prevent the occurrence of the network overfitting, we apply dropout process after the 2 polling layers and the first fully connected layer. The dropout rates are set as 0.2, 0.25, and 0.5 respectively. The next part is the dataset generation and offline training. As shown in Table 2, 5 Fuze German signals are considered in our experiments. Typically, since more than 1 German signal may exist in the real environment, we obtain 10 mixed German signals by superimposing any 2 different signals of the 5 German signals mentioned above. The mixed German signals and the 5 German signals make up a total of 15 German signals. The corresponding labels of the time frequency measures are obtained by one-hot coding in order to evaluate our detector accurately. The occurrence rate is chosen as the measure. Meanwhile, the classification cross-entropy loss function is adopted to improve the occurrence rate. The network model hyperparameters are shown in Table 3. Next is the simulation results and analysis. The recognition performance of the TFAC detector considering the trend dataset with different overlap ratio is shown in Figure 4. It is obviously that the accuracy of the proposed model achieves the highest when the overlap ratio is about 50%. Meanwhile, the recognition performance becomes the worst with a 40% overlap ratio. This phenomenon happens since the time and frequency domain resolutions after STFT pre-processing cannot be achieved simultaneously. Moreover, the overlap ratio affects the quality of the generated images, influencing the model performance directly. In order to achieve a balance between the time and frequency domain resolutions for all of the generated images and the model recognition performance, we choose the overlap ratio as 50%. The recognition performance, the proposed STFT-based and convolutional Wegener distribution-based methods is illustrated in Figure 5. We can see that the recognition accuracy by STFT pre-processing is significantly higher than that of WVD pre-processing because the cross-term interference occurs inevitably in WVD, leading to a low recognition accuracy. In particular, the cross-term interference is more severe in the high SINR region, which causes a decrease in the recognition accuracy. Figure 6 demonstrates the recognition performance of the proposed TFAC and the typical LENET, TFI-CN, and DN detector. It is noticed that the recognition accuracy of the proposed TFAC detector is obviously better than that of the other detectors, especially in the low SINR region. For 15 German types, the TFAC detector can achieve an average recognition accuracy of 99.8% in all the SINR regions. The average recognition accuracy of the DN detector gets the lowest since the DN detector mainly performs global feature extraction at each layer during the training process and does not consider the structural characteristics of the images. In contrast, the CN detector considers the contextual information of the features within each convolution, and the integration of features occurs slowly and orderly. Therefore, the CN detector achieves an advantage over the DN detector in image processing. The LENET and TFI CN detectors perform poorly in the low SINR region because the structure of these two detectors is not sufficient to learn the features of all German signals, which decreases the average recognition accuracy. To give a comprehensive comparison based on the analysis of the recognition performance of the proposed detector. We also further analyzed the complexity of the proposed and exciting detectors. It is described in Table 4. Regarding the complexity of the proposed and exciting detectors, here the running time is chosen to measure the complexity, and 500 images from the text dataset are randomly selected for testing. We can see from Table 4 that the TIV detector has a shorter running time than the TFI detector. Although the running time of the LENET and DN detectors is slightly shorter than that of the TIV detector, their recognition accuracy is obviously poor. And finally, the conclusion. We propose a Fuze jamming signal detector based on time-frequency analysis and convolutional neural network. First, the original jammed Fuze signal is converted into a time-frequency imager by pre-processing, and the jamming signal features can be extracted in the time and frequency domains jointly. Then, the time-frequency imager is input to the TFA detector for jamming signal recognition. Simulation results have shown that the proposed detector can achieve excellent recognition accuracy in both low and high SNR regions. Moreover, the proposed detector outperforms the exciting TFI, LENET, and DN detectors, and achieves a better balance between recognition accuracy and model complexity. Thanks for your attention. Now, welcome any comment or question.